This video is for my pre-algebra classes. It is over lesson 32, probability. Probability is the likelihood of an event happening. When we say an event, we just mean any sort of occurrence. Often in mathematics, when we talk about an event, it could be a certain thing when you roll a die, or a certain outcome when you flip a coin, or pulling a certain color marble from a bag. Those are common events. But really it could be anything happening, where we look at how likely is it. It can also be seen as the ratio of favorable to possible outcomes. And if you imagine that ratio as a fraction, that actually leads to the formula for how we find probability. So first of all, ladies and gentlemen, when you see this right here, you might be tempted to think that this is a capital P times a capital A. But it's not. This is actually something that we're going to deal with more in Algebra 1 that's called function notation. So function notation is where you have something on the outside of the parentheses that is naming what it is we're doing to the thing inside the parentheses. So in some ways you can almost imagine that the parentheses are almost more like a circle or a hole leading into a machine. So where we're sticking something into our machine, our function machine, in this case our probability machine, and we have something else coming out. So this would be read instead of as P times A, this is actually the probability of A. That's how I would read that, the probability of A. So, and if you take your yellow highlighter here, so probability, and this is its formula. So we got a vocab term and we got the formula here. So probability, its formula says the number of outcomes favorable to A. So A would be some sort of an event that we would identify, and basically any outcome that matches A would be favorable. So let's say I'm rolling a die and I say the probability of rolling a 5. Then any outcome that matches being 5 is favorable. Or if I say the probability of rolling an even, then any number that matches being an even, any outcome that matches being even, is favorable. So favorable just means it matches whatever's in here. So number of outcomes favorable to A, or sometimes we just simplify that down to number of favorable outcomes, over the number of possible outcomes. So out of all the different possibilities. And so what we end up with here is a fraction most of the time for probability. So if we consider here, we'll jump down a couple spaces, all probabilities are going to fall between two values. If every single outcome is favorable, so all the outcomes are favorable, then you'll have all the number of possible outcomes on top of the number of possible outcomes on bottom, while something over itself is equal to 1. So the highest probability we can have is 1. And if you think about that, that would mean that every single possible outcome matches what we're looking for. So how likely is it we're going to get what we want? Well, everything works. So we are certain. A probability of 1 means that it is certain to happen. So just to make this clear, the probability here would be the number. Probabilities are numbers, particularly usually fractions. The words here are just what those numbers tell us. So a probability of 1 tells me that something is certain. Now on the other hand, if none of the outcomes are favorable, then your numerator would be 0. So 0 over something would end up being 0. So the smallest probability we can possibly have is 0. And if nothing is favorable, nothing is going to match what we're looking for, then the likelihood that this event will happen, we could say that it is impossible. The probability of 0 means that that event is impossible. It cannot happen. Now if we split this literally in half, and half looks about there to me. A probability of 1/2 then is halfway between impossible and certain. So basically what this means is that it is as likely to happen as it is to not happen. Or sometimes we can simplify that down to as likely as not. So when we say as likely as not, we're really saying as likely to happen as it is to not happen. So could happen, could not happen. It's just as likely it could go either way. Well, ladies and gentlemen, the further we get towards 1, so that the bigger our probability is, the more likely things become. So any probability that falls between 1/2 and 1, we could generally describe these as telling us that the event is likely to happen. It is likely to happen. So if you had something that was almost 1, we could go even further and say, well, if it's almost 1, you could say it's almost certain to happen. If you had something that's just a little bit above 1/2, then it's a little more likely to happen than it is to not happen. The closer we get to 0, the less likely something is to happen. Or we could flip that around and instead say the more unlikely it is to happen. So all the probabilities between 0 and 1/2 could be described as unlikely. And depending on how close they are to 0 or how close they are to 1/2 would determine just how unlikely they are. So in fact, something close to 0, well, if it's almost 0, we could say it's almost impossible. If you had something on the other hand that was just below 1/2, you might say it's a little more unlikely than it is likely. If you had something that's somewhere more in the middle, you might just describe it as unlikely and leave it at that and move on. So these are the range of our different probabilities and kind of what they mean. So if you can fit your probability into this little bit of a number line, then you have an idea of what that number, that probability is telling you. Probability can be written as a fraction, and that's the most common. It can be written as a decimal, or a percent. So I'd like you to take your red pen here and give a nice broad underline here. When you're asked for probability, unless you have other instructions, I want you to write your probabilities as fractions. That is the most common. While a decimal is possible, we're going to put in parentheses underneath here, unusual. While it is a possibility, and every once in a while we do write a probability as a decimal, it is not the typical way that they're written. And finally, percents, we do occasionally write probabilities as a percent. However, usually when we do, instead of calling it probability, we usually call it chance. So, and that's not necessarily a hard and fast rule there, but typically if we're talking probability, we're looking at a fraction. When we're talking chance, we're talking about a percent. And then one of the most common ways you can look at this is if you talk about what is the chance of rain today. Well, if you look at the weather, you might see the chance of rain today is 20%, or maybe it's 50%, or maybe it's 80%. So chance is usually probability as a percent. So ladies and gentlemen, with this basic here, we're going to move on to another of our fundamental basic pieces here, and then we'll actually get to finding some probabilities. So before we get there, though, I want to address one more vocab term called a sample space. And you should have in previous classes learned about this. The sample space is the set. So remember, a set is just a group or a collection of things. We use braces to go around our sets. It's a set of all possible outcomes. Essentially, it's in braces. It's the list of everything that could happen. So, for example, well, before we move on here, so that's another vocab term. Let's highlight that in orange. So let's say we are flipping a coin. So if we're flipping a coin, what are the possible outcomes? Well, I flip the coin, I get heads. Flip the coin again, I get tails. Flip it again, I get heads again. Basically, it's either heads or it's tails. And typically when we're dealing with probability, heads and tails we usually symbolize with just a capital H and a capital T. And that's good enough for me. And so that actually would be a sample space right there for flipping a coin. What I'd like you to do now for me, please, is to skip 4 lines. There's going to be a reason for it in just a second. And we're going to talk about rolling a die. Make sure you skip those lines, though, for what we're about to do next. So let's say we're rolling a die and we want to find our sample space. So you roll a die. What could you get? Well, I could get a 1, a 2, a 3, a 4, a 5, or a 6. That would be the sample space for rolling a die. Now, every once in a while, though, we're going to get something a little bit more complicated. So let's go back up here. This is the reason why we skip those spaces. It's because now we're going to take a look at the sample space for flipping 2 coins. Oops, I forgot my C there. So the sample space for flipping 2 coins. Now, when it comes to flipping 2 coins or doing multiple actions, sometimes it can be very helpful to create a chart to help us make sure that we've covered every possibility. And so what I'm going to do is I'm going to make just a really simple chart here. And so I'm going to go ahead and let this up here represent my first coin. So for my first coin, what could I get? Well, I could get a heads or I could get a tails. And so then let's make our rows then the second coin. And what could you get on your second coin? I could get heads or I could get tails. So if we fill in the box, we'll find all our possibilities. So if this is my first coin, that's if I get heads first. This is if I get tails first. For my second coin, I could get heads second, or I could get tails second. And there are all my possibilities for flipping 2 coins. So I could get double heads. I could get a heads in the first coin, tail on the second coin. I get tails in the first coin, heads in the second coin, or I could get double tails. So we see that there are 4 elements, 4 things inside this sample space for flipping 2 coins. And the chart helped me to find that. So something that comes up often if you are playing games is not just rolling 1 die, but the sum of 2 dice. And likewise here, we might want to go ahead and make a chart for this. So I'm going to come down here. 1, 2, 3, 4, 5, 6. Now if we're looking for the sum, it really doesn't matter which is my first die and which is my second die, because we're just going to add them up anyways. So if I come down and complete these real quick, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 1 plus 4 is 5, 1 plus 5 is 6, 1 plus 6 is 7. Come down here, 2 plus 1 is 3, 2 plus 2 is 4, 2 plus 3 is 5, 6, 7, 8. I think you guys know how to add those. We'll go a little faster here. So that'd be 4, 5, 6, 7, 8, 9. This would be 5, 6, 7, 8, 9, 10. 4 plus 6 is 10. And then 6, 7, 8, 9, 10, 11. And finally 7, 8, 9, 10, 11. And 6 plus 6 is 12. And so if we look in our chart here, we will discover all of the possibilities. And this is kind of a neat chart, at least I think it is, because what we see is these diagonals here where we've got repeated numbers. So that kind of helps me. So I could get a 2. There's a couple different ways I could get a 3, but I could get a 3. I can get a 4. I could get a 5. I could get a 6. I could get a 7. I could get an 8, a 9, a 10, an 11, and finally a 12. And there's my sample space. Now, while this is a sample space, there's a little bit of a problem with this sample space. The benefit of it is it's nice and short to write. So all my possibilities are 2 through 12. But the trouble with it is these are unequal likelihoods. They are unequal likelihoods. If we look at our chart, there's only one way to get a 2, but there are 2 ways to get a 3. In fact, there are 1, 2, 3, 4, 5, 6 ways to get a 7, more than anything else, making 7 the most likely thing here. But if we look at the sample space, nothing in the sample space would give that away. So while this is a sample space, it's not a super helpful one for actually finding probability in a moment. So another way of writing this sample space would be to write it with equal likelihoods. So the way to do that is to represent everything in the chart. So I've got a single 2, I've got 2 3s, I have 3 4s, I have 4 5s, I have 5 6s, so that's 4, 5, 5 of those. I have 6 7s, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, yep, okay. I have 5 8s, I have 4 9s, 3 10s, 2 11s, and a 12. Ooh. And if you think about it, 6 by 6, that's all 36 possibilities there. It's a lot more writing. It's a lot more writing, but now everything here has equal likelihood. Everything there is just as likely as everything else. We're just as likely to get this 2 as we are to get that 3. Though really which 3 it is wouldn't really matter as long as we get our 3, right? So there are 2 different ways to get our 3, it shows. So this here would be the most helpful for finding probability. All right, and let's go ahead and flip to the back. We're going to look at one more sample space here. One more sample space. So we're going to look at flipping a coin twice then, oops, then spin, not sin, spin a spinner. And we're going to pretend that this over here is our spinner. So there's the board it's on, there's the circle of the spinner, and our spinner is broken up into thirds, where one section is A, another section is B, and the third section is C. Now before, the charts that we used, like these, they were nice when there were just two different things happening, because then I could put the first thing that happened and the second thing that happened, or one thing and then the other thing. But this time we've got three things happening. We've got a coin being flipped, we've got a coin being flipped again, and then we've got a spinner. So a different diagram here would be particularly helpful, and this we call a tree diagram. And so the tree diagram starts up at the top, and sometimes I like to just start with a dot. Not that the dot is super important, but I like to. And we're going to branch out to just the very first action. So we think about flipping a coin twice, then spinning a spinner. Well, actually picture that in your mind. Actually imagine doing that. What's the very first thing you do? Well, if I got to flip a coin twice, we're going to have to start by flipping it once. So this first branch is going to be all the possibilities for flipping that first coin. And so either I could get a heads with that first coin, or I could get a tails with that first coin. So this row right here represents that first coin flip. Now from here, each of these possibilities will branch out to our second action. So I flip the coin once, my second action, I'm going to flip that coin again. Well, if you got heads the first time, what could you get the second time? Well, that should be pretty easy, because what you got the first time has no effect on what you get the second time. So the second time I flip the coin, I could still get heads or tails. Well, likewise, if you got tails the first time, could you get the second time? Well, same idea, right? It is unaffected by that first flip. So down here, we are now looking at what happens with the second coin flip. And I want to make sure we understand what's going on with the chart here. If we follow from this dot down to the bottom, we have all of our possibilities so far. So we could have a heads, heads, double heads. We could have heads, tails. We could have tails, heads, or we could have tails, tails. But we have a third action now, because now we need to spin the spinner. So if we spin the spinner, if I got heads followed by heads, what could you get on the spinner? Well, I mean, your coin flips aren't going to affect your spinner at all, so you could still get A, B, or C. If you got heads followed by tails, you could still get A, B, or C. If you got tails followed by heads, well, again, the coin flips don't affect the spinner, so you're still going to get A, B, C on the spinner. And then finally, tails, tails, same thing. So this bottom level then represents the spinner. And so if we follow from the top down to the bottom, we can put together our sample space. So our sample space here starts with a brace. So following it down, heads, heads, A. So H, H, A. Heads, heads, B. Heads, heads, C. So that's all my heads, heads there. So now I gotta go heads, tails. Heads, tails, A is one option. Heads, tails, B is another option. Heads, tails, C. And that is everything that starts with heads. And if you count the bottom of this branch, 1, 2, 3, 4, 5, 6, we should have 1, 2, 3, 4, 5, 6 outcomes so far. All right, now let's get the others. So we should have 1, 2, 3, 4, 5, 6 more over here. So tails, heads, A. Tails, heads, B. And tails, heads, C. Finally, tails, tails A, tails, tails B, and tails, tails C. Just to double check, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 things should be in our sample space. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 things in my sample space. So ladies and gentlemen, now we're going to go ahead and put this together and actually find some probabilities. So we're going to start off real easy. Capital H stands for heads. So probability of heads means what's the probability of flipping a coin and getting heads? Well, again, probability is a fraction. So if we think about the sample space for flipping a coin, how many are favorable here to being heads? Well, only one of them. This is the only thing that matches being heads. Out of how many possible? 2 possible. So the probability is 1/2. One favorable outcome out of the 2 possible outcomes. What's the probability of tails then? Well, likewise. There's only one favorable, tails, out of the 2 possible. So what we see here is it is as likely as not to get heads. It is as likely as not to get tails, because of course they're the only 2 options. If, on the other hand, we go to looking at the possibility of getting double heads, so now we're looking at what happens if I flip the coin twice. So if I flip the coin twice, this is my sample space. So how many of these match being double heads? Well, only this one does. So my numerator will be 1. And then how many are possible? 4. So the probability of getting double heads is 1/4. How about the probability of doubles? So double heads or double tails. So how many match being doubles? Well, this is a double, and that's a double. So we got 2 doubles out of 4 possibilities. So the probability here would be 2 out of 4, which of course reduces to 1/2. So we are just as likely to get doubles as we are to not get doubles. So how about the probability of at least 1 head? So what's the probability we get at least 1 head? So how many of these outcomes match having at least 1 head? Well, this has at least 1. That's 1. This has at least 1. That's 2. This has at least 1. That's 3. This doesn't have any, so no. So there are 3 favorable outcomes out of the 4 possible. So the probability of getting at least 1 heads is 3/4. So if you were to take a coin and flip it twice, you can expect to get at least 1 head in that double flip 3/4 of the time, approximately 3/4 of the time. So let's take a look now at our die. We're going to specifically look at the rolling the double 2 dice. So I want to know, what is the probability then of a sum of 5? So a sum of 5. So if we look at the sample space, we would want to use the helpful one, or we'd want to use the chart. So if I use the helpful one, I've got 1, 2, 3, 4, 4 that match being a 5 out of 36 possible. So 4 are favorable, 36 are possible. And of course 4 goes into both of those. So the probability of getting a sum of 5 is 1/9. So if you're playing a game and you in particular need to roll your 2 dice and get a 5 out of them, they need to add up to 5, you can expect that to happen about 1/9 of the time. So not super likely, but it's possible. It's definitely possible. So if I asked you then instead for what is the probability of a sum greater than 9, a sum greater than 9, then if we look at our sample space, well, 10 is greater than 9, 10 is still greater than 9, 10 is still greater than 9, 11 is greater than 9, 11 is greater than 9, and finally 12 is greater than 9. So we have 6 that are favorable out of the 36 that are possible, and of course that reduces down to 1/6. So 1/6 of the time approximately we should get a sum greater than 9. All right, we're going to now take a look at our little activity up here. So probability of, let's say, getting A. So if this is what we're saying, then since we didn't mention what we're getting on the die, or on the coins, excuse me, that means we could get anything on the coins. The coins don't matter. All that matters is we end up getting an A on the spinner. So if we take a look at our sample space, how many of these things have an A? So there's 1 that has an A, there's 2, there's 3, there's 4. So there are 4 favorable outcomes that have an A on them out of, remember, the total 12. So reduce that down, and about 1/3 of the time we can expect to get an A. Let's say in this case we ask for what is the probability of at least one tail. At least one tail. So this doesn't have any, that doesn't have any, that doesn't have any tails. This does, so there's 1, 2, 3, 4, 5, 6, 7, 8, 9 of them have at least one tail. Out of the 12 possible, so the probability is 3/4. Okay. Let's get a little more particular here. Let's say, what's the probability of getting double tails followed by a C? Well, how many of them match being a double tails followed by a C? Well, just this one outcome. So since it's only that one outcome out of the 12 possibilities, it's 1/12. So we're going to finish off here with the probability of just a single die. So with a single die, what's the probability of rolling a 5? So again, if we look at our sample space for rolling a die, how many of these match being a 5? Well, only that one matches being a 5. So only one of them is a 5 out of 6 possibilities, 1/6. What is the probability then of rolling a 2? Well, likewise, only one of them is a 2 out of the 6 possibilities. If I asked you instead, what is the probability of rolling something less than 4? So 1, 2, and 3 are less than 4, so that's 3 out of the 6 possibilities, or 1/2. If I asked you the probability of rolling a prime number, I would imagine many of you would take a look at the sample space and you would tell me that it is 4/6. And unfortunately, you'd be wrong, which is why I wanted to bring this one up. Remember that a prime number is defined as a number that has exactly 2 factors. So 6 has 1 and 6, 2 and 3. That's got 4 factors. That's definitely not prime, it's composite. 5 only has 1 and 5. That's prime. 4 has 1, 2, and 4. That's composite. 3 is prime. It just has 1 and 3. 2 just has the factors 1 and 2. But the number 1 only has itself as a factor. That's only one factor. It does not meet the definition of having two factors. So 1 is not prime. So the only prime numbers here are 2, 3, and 5. So there are only 3 favorable out of the 6 possible for a probability of 1/2. So what is the probability, let's say, of rolling a 7? So probability of rolling a 7, if we take a look here, so how many are favorable to a 7? Well, none of them. The moment you see something like this and you realize, wait, that can't happen, that's impossible, you automatically know that the answer is 0. The probability here is 0. You cannot roll a 7 on a 6-sided die. For that matter, if I asked you what's the probability of rolling something less than 7, if you take a look at the sample space and you realize that everything is less than 7, that means you are certain to get something less than 7, so therefore your probability is 1. So if you ever run across something that's certain, you automatically know the probability is 1. And ladies and gentlemen, that is probability. However, that is not where our lesson actually ends. Our lesson continues on to something related to probability called odds. And odds, instead, are the ratio expressing the likelihood, oops, I forgot the word the likelihood of the event happening. So how likely it is to happen compared to, now I want to pause there, because if this was probability, we would say compared to all the possible outcomes. So what could happen? So instead, but this is compared to not the possibilities, but compared to it not happening. So whereas probability is a ratio of favorable to possible, we can think of odds instead as the ratio of favorable to unfavorable. And typically odds are written with a colon. So if we think about flipping a coin, if I ask you what are the odds of getting heads, well, the odds of heads are going to be how many possibilities are favorable to heads. So how many match being heads? 1. Compared to how many do not match being heads? Well, 1. So one of these is heads, one of these is not. It's a 1-to-1 ratio. The odds are 1-to-1. Likewise then, what are the odds of tails? One of them is a tail, and one of them is not. Those are the odds for flipping a coin. So if I asked you what are the odds of when we're flipping 2 coins getting double heads? Well, how many of them match being double heads? 1. How many do not match being double heads? The other 3. So this is a odds of 1 to 3. So that second number there, instead of being the rest of the, being all of the possibilities, is the rest of the possibilities. So what if I asked you the odds of flipping those 2 coins and getting doubles? So how many of these match being doubles? We got double heads and we got double tails. That's 2 of them. How many don't? The other 2. So the odds of doubles is 2 to 2. Now the thing about ratios is that they can be expressed as fractions. And while we're not expressing them as fractions right now, the same things that we'd have to do with fractions we have to do with our other ratios, which means we have to reduce this. So a ratio of 2 to 2, well, if I divide both of those by 2, means that this is really a ratio of 1 to 1. So we must remember to reduce our ratios. If I ask you, looking at the rolling 2 dice, the sum of 2 dice, the odds of a sum of 5, well, remember we found that probability up here, right? So there were 4 of them that matched being a 5. Oh, sorry, that wasn't supposed to be a colon, that was supposed to be an equal sign. There we go. Here's the colon. So 4 of them match being a sum of 5, but it's out of 36 total, so therefore 32 of them must not match. Well, now obviously 4 goes into both of those. 4 goes into itself once. 4 goes into 32 8 times. So if you're playing a game and you need to roll 2 dice and they need to add up to 5, and so you now know that the odds are 1 to 8. This means for every 1 time you get what you want, you should expect there to be about 8 times that you don't. Approximately. It's gonna, over time, that's what it's gonna be. Now you can get clusters of 5 every once in a while, but in general, for every 1 time you get what you want, you expect it to fail 8 times. And that's what odds of 1 to 8 mean. So what are the odds of a sum greater than, let's make sure that looks like a greater than, not a 7, greater than 9? Well, again, we could use our probability to help us out. We already know that there are 6 that are favorable to this. Now, if there are 36 possibilities, well, then how many don't match? Well, 36 minus 6 means there must be 30 that don't match. 6 goes into each of these. 6 goes into itself once. 6 goes into 35 times. It's a 1 to 5 ratio. So for every 1 time I get something, a sum greater than 9, I expect 5 times, about 5 times I'm not going to. Finally, if we take a look at our last sample space, the odds of spinning that A, so flipping the 2 coins, spinning the spinner, and somewhere in there getting an A. So we already know that there were 4 that were favorable compared to 12 total. So, well, 12 minus 4 means there are 8 that aren't favorable. 4 obviously goes into both of those to give me a ratio of 1 to 2. For every 1 time I get that A, I'm going to expect there to be about 2 times that I don't. And then last one, let's say we have the odds of getting that TTC. So again, we knew that there was 1 favorable out of 12 possible. So 1 favorable then, and then, well, if there are 12 possible, 12 minus 1 is 11, so there must be 11 unfavorable. And that, ladies and gentlemen, is odds, and that is the end of this lesson.